Hey everyone. In this video, I'm going to be talking about multiple linear regression. On the last video, we talked a little bit about simple linear regression. A lot of what we do for multiple linear regression and simple linear regression are exactly the same. The fears, the assumptions, everything that we have behind it is exactly the same. The difference is with multiple linear regression, we now have to worry about are we putting in enough variables? Do we have too many variables in there? Do we have not enough variables in there? And try to figure out, okay, what the heck is actually going on? With simple linear regression, because we have y equals mx plus b, or y equals beta 1 times x plus beta 0, it's really easy. All the variability that X can account for is used, and then you go from there. Unfortunately, with multiple linear regression, a lot of things that we need to worry about um, that actually do come up are we may actually have a couple different variables that almost or kind of explain mostly the same thing. Which one of those do you choose? Just as an example of this, if we're talking about what's called BMI, so body mass index, it is calculated from the height of a person and the weight of a person. So if you have someone with a high BMI, that basically means they have a high body weight for their size. So if we're looking at, say, weight of a person versus, say, BMI of a person, those two can be highly related to each other, which can give all sorts of issues that could come up. And then there's all the other stuff we need to worry about. I know, horrible. But let's take a look at it real quick. So, and this is going to be probably a bit confusing or even more confusing than before, but that's pretty much just how the way these things work. So with our simple linear regression, we have y equals this mx plus b, which I said was going to be beta 1 times x plus beta 0. For multiple linear regression, we're going to have y equals beta 0 plus, say, beta 1 x1 plus beta 2 x2 plus beta 3 x3, and so on. With all of these, we're going to be doing the hypothesis tests where we're looking at, say, beta 0, beta 1, beta 2, beta 3, and however many more variables we're looking at. These are going to be equal to 0. The alternative is that these are not going to be equal to 0. So which one are we going to choose? Sometimes we'll choose down here. Sometimes we'll choose up here. We honestly really can't tell. And what's going to be going on here is, again, if we've got total variance of our data, let's say this big box, for every variable that we look at, every variable that we put into the model, it's going to take up some of that variance. And when we look at the x squared value, it's going to basically come down to looking at how much variance is accounted for here, how much is here, how much is here, how much is here, and all these other dots. Add them all up, and then there you go. When we're using multiple linear regression, well, with simple regression, we look at r squared. With multiple linear regression, we actually need to look at R squared adjusted. And a couple things that are going to happen when we're dealing with this multiple linear regression stuff is now I'm actually going to show you some data where we have when we talk about independent variables, we have 100 of these. Dependent, we only have one. So what we're trying to do is look at and figure out of these 100 independent variables, which ones are actually useful in trying to predict the one variable that we're interested in. With the data set that I'm going to show, this is data that I actually created, so I actually know what the answer is and can go with that. But one of the things that, or several of the things that are going to come up is just because I have 100 different things I can look at, that doesn't mean they all have some sort of a really useful relationship with whatever the dependent variable is. With our hypothesis tests, we're still going to be testing all that stuff. And we're going to come up with a rule, same as we did last time. So if we fail to reject H naught for some beta value, beta n, we assume that whatever that coefficient is, and remove that term from our model. So we're going to start out with 100, and our final model is only going to have variables that we believe are statistically significant. So they're going to be the variables that have coefficients that are in this group right here. Everything else, because we assume that the beta value is equal to 0, 0 times anything is 0, so I don't care what that is. Get it out of there, make things easier on us. So, uh, going from there, so if we look at all these, we're going to find that some of these variables have a lot or explain a lot more of the variability than others. There will be some sort of a threshold when it comes to all of these things. Just so if we're looking at data like this, let's say our threshold is that. So if the area of the circle is bigger than that circle, then we would think that it's going to be statistically significant. If it's smaller than that, like some of these, we're going to decide that it's not statistically significant. Now, if we're doing this with SPSS, we have some things to look at. Um, there are methods that we can deal with this that are called enter, backward, forward, and stepwise. Because of a lot of the issues that we were talking about last time, the method that we're supposed to use is enter. This just means we put all the variables in, then eliminate, and do this basically by hand. Okay. Very time consuming, very tedious, but because of some of the issues we were talking about last time, this is the approved method for dealing with this. If we can get away with it, stepwise is actually the next best method for dealing with the data here. What this does is it looks at all the variables and then removes some of the variables and sees how the other variables react, and then removes some other variables, and it may put a certain variable back in or pull it back out again. It's going to try a whole lot of different combinations until it comes up with what it thinks are the only statistically significant terms that should be left in there. Forward and backward are a bit weird. With forward, basically, you start with no terms or no variables. So no variables. Then add largest, next largest, etc. And we look at whether or not these terms seem to be statistically significant. So if we look at the information that we have up here, what would end up happening is we'd have, say, x4 come in, then x2 come in, then x1 come in. And then even though if this is smaller than our threshold, we'd add in x3, and then it would look at that and say, nope, that's too small, and actually get rid of it. And eventually it would tell us that this is the model that we want to go with. We can think of this as forward as only the strong survive. But with these forward models, we need to keep in mind all the issues that I was talking about last time. With the backward, we start with all of them, or with all the variables, and then remove only. So what could happen, and some of the things that actually do happen, is we might have a bunch of variables that just barely meet our threshold. If we're going in the forward direction, like we do here, where only the strong ones get in, because these are barely beyond the threshold, they might not actually get included. With this, we might actually get a bunch that are included that literally do not belong in there. So, or aren't all that useful for us if we look at it from various points of view. So clearly, none of these are actually all that good and all that trustworthy. But a couple other things that we need to be worried about here. On the last video, I added in that collinearity, and we're looking at VIF. VIF should be less than 5 for most models, depending on what it is we're dealing with. I've actually had some models where this number was really, really large, but that's just how those types of models work. Can't do anything about it. Uh, with the VIF and what this collinearity thing is. So let's assume that we've got our variance. And like I was saying, we've got one variable, and let's say we call that the person's weight. And then we've got another variable in here. We're going to call that BMI. You can see that these two things actually cover or uh, explain quite a significant amount of the same amount of variability. With something like this, we might end up having something that violates this VIF. Both these technically, if our threshold for being significant is, say, that, both of these, even if you take out the other portion, it's going to be bigger than this because we have this collinearity, because we have this large VIF. In a case like this, we would choose BMI or weight. There are other issues that come up too. Um, and this is something that I've actually seen before. We have this one variable that's out here, and then these two variables are explaining a lot of the same variabilities. This other variable, and all three of these are going to have a major issue on VIF and all of that. Depending on which order you select these, one of the bigger outer one might be the one that goes in first, in which case these two will not be chosen because they're so related to this other variable, they don't count anymore. Or you may put in BMI and then you put in weight, and then you notice that the area for this other thing that's out here is still going to be bigger than this. So we'd actually have all three things get chosen if we're using, say, a backward method or a stepwise. So these can be some of the issues that we need to deal with. These are some of the things that are going to come up. There's also going to be another issue where we can actually have spontaneous, uh, something called spurious correlations. So when we're dealing with multiple linear regression, we're going to be looking at, do a bunch of these variables seem to correlate with y? So we look at basically a variable x1, does it correlate with y? X2, how does that correlate with y? And so on. Well, imagine we've got some variables, and the data set that I'm going to look at, all the variables that are the wrong ones are start off with a W, and you'll have see that W or some of these W's correlate with Y really well, but these are the wrong variables. It's just something that, because of how the data is, because of how the model is, you're not always going to get all the variables you think you should. And in a lot of cases, you could end up getting some variables that shouldn't be in there. And these are going to be those spurious correlations. How can we tell the difference between a spurious correlation and something that actually belongs in there? The answer is you can't, unless you know the data very well. The data that I'm going to show you, this is again data that I made just so I could show that this is type of thing is happening. But if we didn't know that this was happening, there basically is no way that we can work around this and try to figure out, is that truly a spurious correlation, or is that, say, some new thing that just popped up? Oops. So one of the big issues that we can have when we're doing these types of things is, just as an example, a data set that I've worked with before. We're looking at it, will the person have heart disease? And we're looking at things like, what is their cholesterol level? What is their blood pressure? What is their heart rate? Do they smoke? What are these other variables that happen to be in the data set? And we're trying to correlate all these things to our response variable. Now, when we do that, we can do all of our calculations, come up with whatever. But every once in a while, we'll find that something new pops up. So, for example, if I ask you about what do you think are important things when it comes to, say, cancer, one of the things you'd probably say is, like, does the person smoke a lot? Does the person live in a area with a whole lot of pollution? Do they have genes? Blah, blah, blah. But what if, let's say, I had a variable that said how much, or looked at how much celery the person ate in their lifetime, and you see that that has a positive correlation with, say, cancer. Does that necessarily mean that celery has a positive association, which means the more celery you eat, the more likely you are to have cancer in a lifetime. Maybe, maybe not. And it's for reasons like that. And I'm not saying that's actually what's going to happen, but I've done some weird things where I put a random variable in there, just put a whole bunch of numbers in, and all of a sudden that's really, really important. But it's not, and I know it's not because I just made it up, but the software thinks it's important. So one of the things we have to do, and one of the issues that you see happening quite often if you listen to a lot of like science journalism and health journalism and stuff like that, is we may have found something new. We, in the example I was giving, we may have found that celery is somehow related to cancer rates. Okay, why would it be related to cancer rates? And if you ask a bunch of people about that, they could uh, come up with a whole bunch of reasons why that might be true. But all that the data is telling us is that it's something we should investigate. It's not telling us that there is a definite correlation. It could actually be that, say, celery and some other products like that, if you don't wash them good enough, the insecticides and the pesticides that are on them, those are what are, say, is going to give you the cancer later on, not the celery itself. So we need to be careful when we look at these. We can look at some of these and go, yep, that looks good to me. Some of these, you might see something that doesn't make any sense at all, but it's still really important. And just as an example of this, one of the other things we're going to be looking at is something called a logistic regression. With a logistic regression, we're trying to figure out or trying to come up with variables that help us predict whether or not an event will occur. So if we're looking at cancer studies, we're looking at what are the important variables for does someone get cancer? With the data I was looking at, I'm trying to predict whether or not a vehicle is going to come back for warranty repair. And looking at the data and looking at the or talking with the experts on this, um, one of the columns we had, I think, 127 columns and 140,000 vehicles with one column at the very end that was telling us whether or not, yes, we do indeed, or no, we actually do not have a, a vehicle that has come back for warranty repair. Will it come back in the future? We don't know because predicting the future is really hard to do. But what we're looking at is, does there seem to be some sort of an association between the variables that I've got and the outcome of interest, which is, has the vehicle come in for warranty repair? And from talking with the experts, one of the columns on there was just on there because it's on there. It has nothing to do with anything. So of course that ended up being literally being the most important thing. And what ended up happening is I looked at the data and I said, you know what? Let's try everything. Does because the worst thing that's going to happen is you prove someone correct. And literally looking at the data without this one particular variable, none of the models were actually really good at doing anything. Then we put in this one variable, and all of a sudden I could predict 80% of the vehicles that have come back for warranty repair. So I went from nothing to the one variable being able to predict a warranty repair. And it had nothing to do with, say, any of the parts. It wasn't that, say, a manufacturer made a faulty part and that one faulty part or that one lot of parts was faulty, therefore, blah, blah. No. The thing that was important, the day the vehicle was made. And when you look at the dates when these vehicles were made, the dates did not make any sense. If any of you have family that say work in automotive plants anywhere in the country, you know that say for a week or two over the summer, and then in general, the week or two right around Christmas and New Year, everyone's got those off. So there's no one working in the plants. But according to the system, a bunch of vehicles were produced on the week between Christmas and New Year, the time when the plant's not even open. So how do you produce vehicles when when the plant's not even open? Well, it turns out that data production isn't actually the date it was produced on, it was the date the vehicle actually left the grounds from the factory. So what does that mean? It means that they literally had these vehicles. They thought there was something wrong with them. They put them off in a corner. And then over Christmas break, they had a company come in and check them all out just to make sure that they were fine. And then the company that they hired said, yeah, these are fine. Go ahead and sell them. And 80% of those vehicles are the ones that came back for warranty repair. That was it. That was the only thing that made any sense. And with that information, the gentleman that I was working for and people that were uh, actually giving us the data were able to take that data and go back to the company that was supposed to perform those tests to make sure that everything was right, and just basically said, out of 130,000 vehicles produced at my plant, we gave you 200 of them, and we were wondering if they were broken or not, or would come back for warranty repair under a certain cost, and not all warranty issues. 160 of those 200 came back for warranty repair. Out of the 130,000 plus that they didn't touch, zero came back for warranty repair. So sometimes a variable will come up that shouldn't be, um, but it is. And even if you've got really, really good reasons why it can't be, sometimes it still will be. So with that, let's take a look at a potential data set here. So I'm going to open SPSS. I'm going to share my entire screen. So we can see a bunch of things that I've got popped up here. I'm not actually going to use any of those. So I'm going to go to File, Open, and then Data. And just trying to think of where I actually saved these. So I believe it's Documents and Stats Data. And I need to change these to Excel. So that might not be it. Sorry. Go back to Documents, Stats Material, Lab 8 and 9. So there we go. So looking at the data that I have here, assuming that everything works out right, and assuming that SPSS pops up again. All right, here we go. So I've got some of these variables here that are just labeled as R1 through R6. These are the right variables. These are what I should be getting. The W's here are all the wrong variables. And just to show you what all of this is going to look like, you can see that there are columns and columns and columns of this stuff. So we're actually looking at 50 different variables W1 through W44 are the wrong variables. They do not belong. They should not be there. R1 through R6 are the right variables. And then I've got Y1, Y2, Y3, and some other stuff here. So what I'm going to do is we need to do a multiple linear regression with these. So I'm going to go to Analyze, Regression, Linear. For this one, I'm going to say that my dependent variable is Y1. My independent variable is going to be W44 through R1. And just to show what happens, I'm going to leave this method here as enter. With statistics, I definitely want the collinearity here. Something that might help you understand what's actually going on here. Not necessarily something that, say, a true professional would need, but might be useful for all of you to look at a R squared change, see what's going on. Sorry. And then we look at plots, histogram, normal, produce all. Let's see if it actually tries to produce all. Save a lot of stuff here. Don't really need to worry about that. I'm just going to go ahead and click on OK. This is going to take a moment. So if you look down on the bottom here, you can see where it says running regression. That means my computer is actually thinking. And while it's thinking, you might be able to hear the cooling fan speeding up. So now here it goes. So these are all the variables that we put in. This is telling us everything that was entered. We can see that the R squared here was 0.99. R squared adjusted is 0.99, standard error, and so on. And then here we can look at all of these. And the thing that we need to be worried about when we're looking at a lot of these is literally this VIF column that I've got here. So we can see that all of these are 1 point something something. Cool. That means that we don't have all those variables like I was showing with weight and BMI where they overlap quite a bit, which is what we want. If these values do get high, what actually happens is uh, the standard error for those terms will actually get fairly large and make it harder and harder to figure out whether or not a term is actually statistically significant or not. Looking at what we've got here, we can see the significance level of all of the R terms is well below 0.01. Both some of these other ones, like looking down here, it's a W11. Technically, the significance level here is below 0.05. So if we didn't know any better, we'd probably want to add this one into our model, even though it shouldn't be there. W14 looks like it might be statistically significant. Here is W19, W23 looks like it's close to being statistically significant, but not quite there. So some of these, anything that we see in the W here, these are those spurious correlations that I was talking about. So what we should be doing is looking at the significance levels here, find the variables that have the largest values, and then eliminate, say, one or two of them at a time and go on from there. So that would be cool. If I use some of these other methods here, so if I go back to regression, I got everything set up, but this time I'm going to use stepwise. Now that I'm using stepwise and I click on OK, again, it's going to take a little while. You can see down here that it says running regression. All right, there it is. And what it's done is it's decided that W or R1 through R6 are all statistically significant, but it's also choosing W11, W19, and W36. So again, these three are the statistically significant terms, but these are also those spurious correlations that I was talking about. They do not belong, but if we didn't know any better, we would look at them and think, hey, those actually look like there's something important. When we go and we look at everything that we've got down here, as we're changing the models, you can see uh, adjusted R squared changes quite a bit versus a R squared. And at the final model here, R squared and adjusted R squared are about the same, which is, well, what we're going for. This should be close to each other. Then coming down here, blah, 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 to this last thing here. Everything that's down here is essentially everything that should go into the model. So according to this, the model that we have is y equals 6.028 plus essentially 5 times R1 minus 3 times R2 plus 10 times R5 plus 1 time R3 minus 1 time R4 minus 5 times R6 minus 0.008 times W11. Are those, no, that's a decimal point, sorry. So 0.008 times W11 plus 0.002 times W19 plus, I guess those are negatives, sorry. And then plus a 0.079 W36. So that is a lot different model than we had before using the enter method. If I come back up here, go to analyze, regression, linear, go from stepwise to say remove. Let's see what happens. One of the weird things is when we use these different methods, we can from time to time actually come up with totally different answers. So let's see what we get here. R1 through R6 are important. W11, W19, and W36, those still look like they are statistically significant. I believe that's the same thing that we had before. So looking at our final model again, the same thing that we had before. If I go to analyze, regression, linear, let's say we go forward. Let's see if I get some different values this way. Get to sit around and wait and wait and wait. And again, it's telling us that all the same variables are statistically significant here. So that's cool. I can go back, and because I've got some other things that I can actually test here, instead of a Y1 here, I'm going to swap it out for, say, Y2. And say I've used stepwise regression again. Again, if we're looking at these, I prefer to do stepwise. You shouldn't be using any of these methods other than the enter method and then hand selecting everything. I'm too lazy for that. So let's go with stepwise and see what's going to go on here. Data's running, 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 running. There we go. So here we have R1 through R6 all look like they are statistically significant. And this time, W27 and W28 look like they are also statistically significant. But again, these W's do not belong. They are the spurious correlations I was talking about. But if you don't have data, or if you don't know what the data should be telling you, you probably would look at that and say, all right, that looks good, and go with it. If you have that expert there to tell you, oh, those can't be part of it, maybe you need to listen to them, maybe not. So, like I said, I solved the problem with the data by completely ignoring what the expert said, because sometimes they're wrong. Looking at the chart here, so standardized residuals, does that look like a normally distributed plot? Yes, it does. Do all those data points look like they're on the straight line? Yes, they do. So we can see R1 and how that looks. R2, we see that R3 has quite a bit more variability in it, but we can still see the upward slope. R4 downward. R5 and R6 are what are called dichotomous. So that's why they're just the things at the end. Then looking at this one, this is kind of telltale here. From a statistical significance point of view, this is important. But could you draw a straight line through that and find an upward trend or downward trend? I can't. It's not blindingly obvious. So this is a potential thing here where we can look at that and say, well, I don't see an obvious trend in here, and it was small anyway. And actually come back and why is W27 statistically significant? Well, it's because there's 30,000 data points that we just looked at. So the more data points you have, the more chances you have of finding some of these spurious correlations. And even if you don't have that many, you can still find spurious correlations. And it could actually be easier. So there's no way around it. You just need to learn how to deal with it. But anyway, here's the same thing for W28. Last time we looked at this and tried the residual homoscedasticity test. So let's do Y2 as our dependent. I've actually never done it with this stuff before, so let's see what happens when those are the independent variables. Click on OK, and yeah. So it's coming up with all the statistically significant things. And then it's actually telling us that we're like kind of getting close to having a statistically significant non-constant variance. Maybe we should be worried about that. Maybe not. But anyway, when you look at all these different methods, I prefer to use stepwise. And essentially what it's going to do is stepwise is there to help you eliminate variables that do not belong. And they do not belong if they are not statistically significant. If they're not statistically significant, we assume that the coefficient or the impact that they have on the model is zero. Since zero times anything is zero, when we try to be concerned about whether or not it's important for the model, no, it's not. So I will leave it at that and talk with you all later.